supposed us to give permission. I think I just uploaded what is that? An update.
Okay.
Okay, I have the Zoom Professional. I can't see myself, man. Man, are you able to see me?
Yes, sir.
Anyway, let's get going. How do I see myself? Oh, because there are too many people now. Huh? It says Balaji Chakravarti is talking. All right, okay. So, suppose there are thermocouples and there are 5 temperature measurements, and I know that it is a one-dimensional. So, let's say the challenge is to get the Q. Okay. So, this Q equal to yesterday's. Somebody also, one or two students also wrote that this is possible with the Fourier's law. Okay. Let us say that K is known and A I am giving you. Okay. This is the A. So, this is the A I am giving you. So dt by dx, unfortunately dt by dx, if it's linear, I need only 2 points to get dt by dx, but I've got too many points and all these temperatures have a error. For example, if the temperature is like this, if the temperatures are like this, a straight line cannot pass through five points. So there is a temperature, there should be some line like this. I don't know what that line is. If I connect all the points, it is coming like this. So dt by dx is based on which 2 points? So this is a fundamental dilemma, which you will never learn most of the time in all the courses, engineering, mechanics, science of materials, physics, one maths. So it's a perfect world for you. So all professors will teach you classes. There'll be exam. The question will be perfect. There'll be only one answer, and whatever the prof says is correct. And the world is not linear like this. World, you have to go to a factory and some problem will be not properly put. You cannot go and tell him the question paper is incomplete. I cannot complete. Boss will say you're a graduate from IIT. Just figure out. So we should learn to deal with incomplete problems. We should learn to deal with scanty data. We cannot say data is not available. Data is not available is basically all through your lives. You are writing only exam. Question paper, A is the question. Highest marks, exam, grade. Life is not like that. I make 5 temperature measurements. I want to know heat flux because knowing the heat flux is more important than solving the problem in the exam and getting the grade. Because I want to design a system. Okay, that is for satisfying somebody. There is a universal system. There is a prof. You will give S grade, A grade. That's all okay. Fine, it's very good. But so the problem to deal with in real life will not be posed like this. Real life, when you go to the company, nobody gives you question paper every day and asks you to solve. Nor will everybody every day you will get brain teasers. Like it will be sometimes the work will be challenging, sometimes the work will be boring, sometimes it will be repetitive. Boredom will be an integral part. Dealing with boredom is also important. Just like lockdown has taught you how to deal with boredom, how to deal with loneliness. Okay, like that, how to deal with an incomplete problem. Otherwise, we call whatever problems we are giving in the question paper, we call it as textbook problems. Textbook problems are rarely encountered in life. Now I have 5 temperatures. They are going up and down like because each thermocouple has a dharma. It will behave according to its dharma. So there is an error. So I want to find out what the heat flux is. This is a challenging problem. Alternatively, I can say so many watts per meter square. I will say this is given. Now turn around and tell me what is the thermal conductivity. So here the inverse problem here in this case is an estimation. I want to estimate. So estimation is a very important aspect in life, more than analysis. Somehow we are obsessed with analysis. There is a differential equation I want to solve. I want to integrate. I want to differentiate. Life is not only about differential equations. Sometimes there may, as Professor Balaji told you, sometimes there may not be a forward model. There will be a lot of data. I may have so much data about heat exchangers. I may have so much data about breast cancer patients. So forward model, differential equation, question paper, forget about all that. I have a data in the cancer hospital last 20 years. Okay, I know something about radiation. I know something about heat transfer. I know something about biology. Can you do something? So can somebody, as a preliminary screening, based on this data, can you come up with some model or algorithm or something? And a new CT scan or MRI is taken. Can there be some screening? Doubtful, clear, diagnosed, likely to be cancer. Then only these, the screened out things need not be again shown to the doctor because the doctor's time is important. So we have to solve problems like this. That's why data science, all that is picking up. But if you just concentrate only on data science, because everybody will say I am data science, but you should not only have have fundas in data science, you should have your domain competence in general engineering or in heat and thermal sciences or in civil engineering. So if you can combine the domain expertise and the data, big data, MI, MLA, all that, it will stand you in good stead. Now we have to do something about this. Hurry. That is a problem. Okay, so phone will come because nobody is, they wouldn't know that I'm teaching a class from my office. Okay, so we are concerned with estimation. The estimation could be the estimation could be a boundary condition. So this boundary condition is basically heat flux or a heat transfer coefficient or whatever, or it could be a property. So this could be this is a mathematical model, so to speak. There is a model, there is a measurement, there is something to be estimated. So in this, I should bring this framework of inverse. What is this framework of inverse? One possibility of this framework of inverse is basically, if Q is given, I want to find K, I can solve the heat transfer problem by assuming K1, K2, K3, K4, K5, K6, K7, K8, and generate some temperatures synthetically or numerically. I solve, I analyze and solve, and then get these 5 temperatures at these 5 locations. Now I will turn around and see, compare these 5 simulated temperatures with the experimental temperatures. And I propose that there is an error because the K, which I am using, K1, K2, K3, they're all guess values. It is unlikely that I will hit upon the correct value of K. So if we take 20 samples, what are the samples? K1 to K20, and then solve this heat transfer problem, I can get 5 temperatures each. So for 20 samples, I will generate 100 temperatures. Okay, each K with 5 temperatures. Based on this, I have to propose. I have to propose a framework. I have to propose a framework wherein I will do something and say that among the 20 samples, this value of K is most likely to be the answer. So that is why it is an estimate, because that is not the truth. Truth is a very difficult concept. Don't think that the 30.1 degrees thermometer measured, it is the truth. Thermometer can go only up to 0.1. The truth can be further beyond. If there is some other device which is having a 0.01, whatever the thermometer is telling is not truth. Truth in philosophy or truth in general is a very difficult concept. Once you get into this idea of truth, you will go mad because we don't know where the truth is. Because truth depends on the instrument, it also depends on the subject, who is measuring it. If I have no idea of a thermocouple, I will make a lot of, if I have no idea what the errors are there, even if I have a thermocouple, I don't know how to measure. You will say that it cannot be measured, there is no truth. A heat transfer professor will measure it differently. Sociology professor also will not know how to use this thing. But I may not know model in sociology. So please don't think objective. Most of the things are not objective. It is subjective. Okay. You are thinking grade is objective. Grade is also subjective because I am giving an exam. There is a subject who is giving an exam and saying that if somebody gets 85 marks, he is getting S grade. If some other professor sets a different paper, the grading will change. So we are obsessed with this idea of objective, subject, everything is subjective. At the end of the day, everything, very few things are objective. Okay, let's not get into that philosophy. Now, with that 20 samples, I'll be able to go closer. Now, my belief system is, which are the 20 samples I will choose? Whether I will choose all the samples from 0 to infinity, then you're not an engineer, you're just a mathematician. I can choose K equal to 0.001 to K equal to 80,000. Mathematician will say 0 is less than K less than equal to infinity, right? Because it is mathematically correct. Thermal conductivity cannot be negative. Thermal conductivity has to be between 0 and infinity. It is the most unimaginative for an engineering problem. Let it be mathematically correct. Who cares about whether it is mathematically correct? I know it is a metal, and I know heat transfer. I know metals, the K varies from 10 to 500 or 600. So I will choose the samples from 10 to 1000. That is your engineering. That is your belief. That will make your estimation better. Instead of, if you take one sample at 0.1, next sample at 10, other sample 100, 5000, when you go take samples at 500, 1000, 2000, 5000, all are waste. All are mathematically correct, but engineering is waste because there is no material which is having K 1000 or 2000. There is no material which is having 10 to the power of -4 also. So what are the bounds? What are the reasonable samples? For that, you should have a subject knowledge. Just because you know how to solve the problem mathematically, it doesn't solve the problem. Finally, you have to do an estimate. You have to do an engineering estimate of the problem. Therefore, common sense is very important. Common sense, prior knowledge. You have an idea of what the material is. That is very important. Everybody need not get the same answer. The smart one is entitled to get a better answer. Somebody who's an expert in the subject will get a better answer in a shorter time. That is the way nature works. Okay? Everybody has to get the same answer. There is only one answer. It is not correct. That is good only for academics purposes. All right. So this is the framework. So based on some measurements, based on some model, based on some measurements, based on some model, and based on a proposal. The proposal could be to minimize the errors. How do you minimize the error? Whether you'll take the modulus of the error or you'll take the sum of the square of the error, we don't know. So some proposal. So there is an inverse there. Additionally, is there a belief about your quantities to be estimated, or it is too much of a problem that there are more quantities to be estimated than your data can handle? This is called ill-posedness. Whether small errors in temperatures will cause large changes in your estimate of K, all these are issues. Because of these issues which are plaguing inverse problems did not see the light of the day till 40, 50 years back. Though 100 years back, people knew that inverse problems were important. So inverse problems have grown. Inverse methods have grown in the last 30, 40 years because we now have powerful computers, we have software packages, people know how to handle large matrices, data, and all that. And also we know methods to what is called regularize. What is regularize? If something becomes unstable numerically, we know how to regularize it so that we can do some estimation. All right. This is the broad framework. I now use a PowerPoint presentation to just discuss about the course content and some interesting problems. All right. Okay. This can be minimized. Okay. Now, where is this? Share screen. Share screen. Okay, very good. Are you able to see this? Anybody?
Yes, sir.
Yes, sir.
Yes, sir. Very good. Okay. You can see me and the correct. You can see me as well as the screen. All right.
Yes, sir.
Very good. Okay. So we are still introducing. All right. Slideshow. Okay. Okay. So, see that how to push. I am seeing myself, Varshini, Srirag. How do I push that to the right side so that I am able to see the full? Anybody knows?
Sir, on your screen there is a triple dot. On that you can.
What dot? What dot?
So you have a triple dot for the options. And then pin.
So you can just drag it and move it away.
Yeah, very good. I did it. Because I'm not able to see the same. Okay. Okay, all right. Thank you. So the principal objective of the course is to give the students an overview of inverse problem. That is the whole idea. So it is basically like an applied common sense with a little bit of mathematics and heat transfer principles, statistics, probability built into it. So it's a way of looking at things differently. Okay. So the principal objective of the course is to give the students an overview of inverse problems in heat transfer and ways of formulating and solving them through examples. Since all of you are fresh from heat transfer, either this year or last year, so all the problems will be from heat transfer so that you can get a connect to what is going on. I could have said general inverse problems in science and engineering, where then I have to choose problems from various fields. I myself have not worked in inverse problems in other fields. Therefore, it would be difficult for me to. I would never like to teach a subject where I would like to take from some other book and read and listen, because this is our own course. This is not there in most universities. It is based. I am doing work in inverse heat transfer the last 15, 20 years. So most of the content is basically generated by us. Therefore, I would not like to teach a course unless I have done research myself. That is my take on anything, whether it's atmospheric science or inverse or heat transfer. We became a teacher after we did the PhD. So we conquered the field a little bit. There's There's a lot to be, lot still to be conquered, but that's the way. Okay, so but we have been doing a lot of work on this inverse. So you can talk to Rajesh and Suraj and get more ideas about all this, the kind of work we are doing. Course content introduction, that's what we are doing now. Examples of inverse problems with heat transfer. I already told you some examples. We'll have a more structured way of discussing the examples in the later classes. Definitions and difficulties. I already explained some difficulties in the simple problem of a slab with inverse problem. Ill-posedness, different causes can lead to the same effect. And nomenclature, you have to flesh out the nomenclature. What is error? Okay, what is standard deviation? What is variance? What is maximum likelihood estimate? What is the Gaussian distribution? Okay, all those things we'll have to flesh out. So some probability and statistics we have to study. Statistical description of errors. Then treating an inverse problem as an optimization problem. That's very important. And then parameter estimation, function estimation. So we are basically doing estimation. Estimation can be of two types. So one is the parameter estimation. Please look at the board. This K, getting the thermal conductivity, is a parameter estimation. But suppose I give a heat flux. Okay, I give a heat flux to this problem, which is A plus BT. Okay, that means as a function of time. Are you able to see the board? Huh?
Yes,
I'm
sir.
right. I'm writing something on the board.
Yes, sir.
Okay. Okay. Very good. Okay. If you see this board, this paint is coming off. So now I have to do something this weekend, Friday evening, so that Monday it becomes all right. Okay, let's say that you're giving something like this A plus BT plus CT square and all that. If you get ABC, then you are doing a function estimation. That is a function estimation. Okay. If you just Q is a constant and you pull out Q, that is a parameter estimation or a boundary condition estimation. If you're just pulling out one value of K from all this Jamela, that is called a parameter estimation. But if there is a function which is to be pulled out, obviously function estimation is going to be more difficult than parameter estimation. This function could be a boundary condition, heat flux, heat transfer coefficient, emissivity, or whatever. Parameter could be thermal conductivity, diffusivity, and this thing and so on. So in civil engineering, it could be other thing, right? It could be porosity, permeability of the soil, okay, the permeability of the soil. So in petroleum and geology, it could be permeability of the rock. Okay. In cosmology, it could be the absorption spectrum or the absorptivity or the spectral absorptivity of the gas, the spectral emission coefficient of the atmosphere of that particular planet, whether it is Venus or Mars or whatever. So different subjects, it could be different. Or the signature of the tissue in the CT scan or MRI scan, or that bright spots in a PET scan where somebody is scanning the whole body for cancer. So all these things are basically some of these things which have to be estimated. So the course is split into 3 parts. Leave the first 2 chapters. First 2 chapters are generally nomenclature. Classical techniques, Bayesian techniques, and neural network. So there are only 3 parts. Classical techniques are all based on calculus. Okay. Bayesian techniques are all based on probability and statistics. Okay. I come again. Classical techniques are based on calculus. That will be one part of the story. Some 8 to 10 classes, 10 to maybe 10, 15 classes in that. Bayesian statistics, the Markov chain, Monte Carlo, all that they are based on probability and statistics, about 6 to 8 classes. Then the Metropolis Hastings algorithm is a continuation of that. So if you want to treat it differently, or we'll treat it together, that's about 1/4 of the course. Then 1/4 of the course will be the last: deep learning, neural network, surrogate model, all that. Okay. And the first 8 to 10 classes will be 7 to 8 classes will be all these first 2 things. We have to flesh out all these nomenclatures, this thing. In order to make it less boring, I will also be, whenever we discuss Gaussian probability, I give some basic problem. If somebody is making a shaft and nut and bolt, this is the mean, this is the standard deviation. What is the probability that one bolt will be this much diameter, like that? We'll solve some problems. These are basically like warm-up exercises. All right. Very good. Okay. Classical techniques, I won't go deep into this technique. Basically, you have to get some sensitivity coefficient. That is, what is the sensitive. So I'm looking at dt by dk. It is not dt by dx. If k is to be estimated, what is the sensitivity of the temperature to thermal conductivity? So if there are many temperatures and many parameters, dou Ti by dou K, dou alpha J or dou AJ, where A is the parameter and T is the temperature. So you can make it as dou Y by dou Z, dou Y by dou X, and each of this Y and this thing has got various components. So it will be a matrix. Finally, it will be a matrix. Then we'll look at the Liebenberg-Marquardt algorithm, the method. Then Tikhonov is the person, Russian scientist. He is the father of this inverse, this thing, where he figured out that you can add a term to this minimization of errors by which this jumping up and down of this algorithm can be reduced. So he is the Guruji of this subject. Alifanov was his student, and Alifanov is still active. He used some iterative regularization. That is too special. If time permits, we'll do that. But all the examples we are going to teach will be from conduction, convection, radiation, because it's an inverse method in heat transfer. Then I'll teach you my favorite, the Bayesian method, where this belief. I told you that belief that this material is a metal, blah blah blah. Why you have 0 to infinity? Can you quantify these beliefs and put it into the solution procedure? That is the idea of Bayesian. Not just saying that I will search only in this interval. That is also Bayesian. That is, I am giving bounds for my search process. It is not a helter-skelter search. Okay, somebody said that. You know this story, right? There's somebody is trying to come on chat. Just drags her. Oh, that is it. You know this story, right? Somebody lost a ring inside the house, and many people were searching. Okay, one family members are all searching. One child was searching on the outside. Then somebody came and asked. Father came and asked, "Why are you searching outside?" He said, "No, Papa, light is available only here." Okay, so we should not do such kind of searching. We should search in that place where it is likely to have been lost. Okay, often because we have an algorithm, we keep on. See, the other thing in English is, if what you have is a hammer, HAMMER. If what you have is a hammer, everything looks like a nail, NAIL. So you want to hit everything. Okay. So therefore, the right tool for the right problem. So you have a assault rifle. You want to use it to kill a mosquito. You have to use it in the border, and you have to use it for killing the enemies. All right. So which tool to use for which problem? So this is very, very important. Okay. Frugality, optimality, and essentiality. All these things have to be taken into account. All right. So, okay. Okay. Metropolis, Hastings, Gibbs sampling, all that. Now it law, everything looks like Greek and Latin to you. Don't worry, we'll flesh all of them out. Basically, these are this chapter on Markov chain and the Metropolis is coming under the field of computational statistics. So, you will learn a lot of computational statistics in this course. I will not call it a statistic. It is statistics masquerading as an inverse heat transfer problem. So you would have figured out posterior distributions, working out estimates, variance, maximum of the product distribution, likelihood. So we will do all that without frightening you with the nomenclature. So there are plenty of statistics in this course, plenty of probability, plenty of common sense, all that. Then the last chapter will be Professor Balaji Srinivasan, 8 to 10 classes. All that is neural network. So if you learn all these techniques, you will be fine to apply this even if you want to get into data science or any other field. These are the core principles, right? So you'll be able to do this. So there are no, unfortunately, there are no textbooks, nil. Okay. Reference books, some optimization algorithms, reference for my own book is there. Now it's going to come out as an international edition in Springer. Okay, next month we just updated that book, and so now I think. Thermal System Design and Optimization, 2019, right? So we updated the book. So this is the second edition. Some copies are available, but the e-copies may not be there. If somebody is very much interested, it's pretty expensive. I think it is about $14.95, but you can get discount. Huh? So A clever way would be to just watch my optimization lectures for free on YouTube or NPTEL. That's also possible. Okay, let's go to the references in order. Beck and Blackwell. Beck is also very old professor, 85, 90 years old. East Lansing, Michigan. So he's also one of the founding fathers of the subject of inverse. So he wrote a book on inverse heat conduction. Gelman. Gelman is a Bayesian and data analysis. So they are all statisticians. And Thaler and Duda, they are heat transfer professors. And the fourth is myself. So fifth, there is a book on optimization. So I'll use some algorithms from that. Then MATLAB. Okay, 5 and 6 are basically what S. Balaji has given. So MATLAB, any MATLAB book, and the last one is about Bayesian filtering and smoothing, which is using for this algorithm. All right. Okay, let's introduce estimation now. We already saw this estimation in relation to heat transfer. I'm generally introducing estimation. In any branch of knowledge, estimation is a fundamental problem. Estimation is often more important than analysis. Somehow, as students, and particularly BTech, MTech, all that, I also come through all this route. Na? So we seem to be obsessed with analysis. We should be able to solve. We should be able to solve. We don't care whether it's a real life problem or not. Mathematical correctness, mathematical exactness. It is overemphasized in school. At JEE, you should get the correct answer, and you should get the correct answer minimum possible time so that you can attempt as many number of questions. Life is not like that. If you cannot finish a project today, tomorrow also you can finish. So life is not a speed test. Okay, nobody is going to. So a lot of things have to change. A lot of educational reforms have to take place. Okay, let's not get into that too much. In everyday life, a family needs to have an estimate of total income and total expenditure. So in order to plan, somebody you want to buy a new house, or somebody has to go abroad. Somebody wrote GRE and TOEFL, like you. Next year, you need some money. Then the family has to plan. Okay, this is the finance. This is which bank we can get a loan. How much of savings are available? If there is a sister or somebody who has to study, or somebody has to be married off, or old parents, and this corona trouble gave so much trouble to finances and this thing. And is there some other family member who has lost a job? All the brothers and cousins are supporting. It has happened in our family also. Somebody lost a job. All the cousins, they created a fund, and correct. So, and also even in campus, all the shops, they all lost their livelihood for 3-4 months. Everything was closed. We all profs and staff, we put some money, few thousands, all of us, and we collected some reasonable amount, 1 lakh or 1,50,000 in all the 15-20 shops, 10K each or 12K each we gave. So everybody has done something like that. The government also said free ration, this thing, and so this has been very troublesome. No, last 1 year. Okay. In any case, this estimate of total income and expenditure is required for the nation. Also, yesterday we had the budget. Your Nirmala Sitharaman, your FM needs to know what is the income, what is the expenditure, and if the income is not meeting the expenditure, you will get a loan. A loan is not free. That loan has to be serviced. That means you have to pay the interest. That will again become an expenditure. So, if your income is not such that you cannot even pay that loan, you will take interest. You will take some more loan to pay that this thing. So it is a infinite do loop. Okay, it is an infinite regress. A company or enterprise needs to know its income and expenditure. Whatever it is, Ather, Scooter, this thing, Amazon, whatever it is, all fancy things. Finally, there is a balance sheet. You see, finally, are you making money or not? We have invested money. Are you making money? Okay, we can wait. 2 years, 3 years, 5 years, you tell the payback period. After that, you have to start making money. Otherwise, the enterprise will be closed. More than that, if TVS is making scooter or Royal Enfield is making bullet, you should have a good idea of the supply of raw materials and demands and this thing, how much labor is available, how about the inventory, raw material, and what about the pushing out the sales, and how about revenue, cash flow. So many things have to be done. So estimation is required at all levels. An engineer needs so many estimates: performance of a heat exchanger, performance of a thermal power plant, performance of a solar plant, okay, running cost, reliability of this equipment, reliability of this manufacturing of the nuts and bolts, okay. Then then estimate of the life of an engineering product. Okay, I'm introducing a new product in the market. How many years I should give after sales warranty, replacement warranty, then warranty only on parts, then warranty on payment basis. Cars, now we have 3 years, 3 years compulsory warranty, 4th year extended warranty. Fridge, TV also now LED TV, 3 years, 4 years warranty. And so all these things require some estimates. All right. So estimation is the goal of the study of any inverse problem. Okay, be it astronomy. What is the estimation in astronomy? You have a lot of this. You have telescope. You can get on the, or you have spectrometer, and then you view, or you get the emission spectra and absorption spectra of faraway planets. From that, you use a radiation heat transfer equation, some equation in physics or heat transfer, and try to find out what are the approximate constituents of the atmosphere. What is the goal? Science for the sake of science, and also science for the sake of figuring out whether any life is possible there, whether if by chance any oxygen is there, any possibility of water being there. So you want to do all this, right? Cosmology, that is as cosmology. You want to do estimation in finance. I want to invest my money. Whether you want to buy a share in HCL Technologies, or you want to buy a share in HDFC or LIC, whatever. So estimation is important. Okay, this inverse methods is one way of looking at the estimation problem. So please be aware. Please be aware that this estimation will trouble you throughout your life. Okay, so whatever be your field. All in inverse heat transfer, the goal is often to estimate properties and/or boundary conditions. I already talked about this. What properties are to be estimated? Properties like thermal conductivity, which is difficult. Density is easy to measure because from high school you know how to measure density. Thermal conductivity is tricky. Heat transfer coefficient is tricky. Sometimes specific heat can be tricky. Thermal conductivity can vary with direction. Then it will be Kxx, Kyy, Kzz. There can also have thermal conductivity can be deadly. Thermal conductivity can be deadly. What is deadly about it? Actually, thermal conductivity is like this. So this is called a 9-component thermal conductivity tensor. So this one is very simple. You thought that life ends here because you thought that see that is sometimes the knowledge, no? So even suppose we got S grade in heat transfer, we thought I know this conduction. You don't know that this is a very special case. Generally, all materials are like that. If these are not dominant and only this is dominant, then that Kxx is considered as K and you leave it like this. So if you don't know this, if you don't have this awareness, you think you would have conquered the truth. I found a thermal conductivity, but you know that it's a very special case. So the actual case is a 9-component, okay, and it is a symmetric tensor where Kij is equal to Kji, and this is called the principal direction. So there could be a case where the next difficult case would be these are all 0. That is off diagonal elements are 0. Then this is called an orthotropic material, honeycomb structure, which is they are widely used in satellites and spacecrafts and so on. So you cannot use your simple Fourier's law. The Fourier's law has to be applied in every direction because Q is a vector. Okay, the heat flux is a vector. Okay, so please remember that. Okay, and thermal conductivity is a tensor. Okay, this is a vector. Thermal conductivity is a tensor. Okay, so thermal conductivity can be very deadly. So in fact, they gave a project. We got a lot of money from ISRO. We developed a high vacuum chamber setup where we got Kxx, Kyy, Kzz from honeycomb material, which is used in satellite. So this is a project we did along with ISRO. This setup is still there. Suraj is doing experiments on that. It is a pity that you're not in campus and you're not able to see that. Suraj himself is in Velachery now. He's trying to enter the campus. So last 7-8 months, he could not enter the campus. He came briefly, went back for some problem. Now he is not able to re-enter. Okay, so that is his story. We are able to go up to 10 to the power of -7 millibar vacuum. Okay, so we are able to do that. So this simply whatever I've written. To get this Kx, Ky, Kz for a material can take 5 years. It can take 50 lakhs or 1 crore of rupees. It may require 2 PhD students and 2 professors or 1 professor who will monitor this. So it is not simple. Q is equal to K. So when you actually go to the field, whenever you want to do something significant, it is not simply like, okay, I learned it, I studied it, I got a grade. It isn't. You have to work. Regardless of how much you know, you have to work. Unless you do something, you cannot learn it properly. A prof like me can come and teach you all that. This is basically to take you to the water. You have to drink the water. Take you to the pond. All right. What boundary conditions are to be estimated? This boundary condition could be heat flux, heat transfer coefficient, or I want to know what is the T infinity here. If there is a T infinity here, okay. If there is a contact conductance, there may be so many boundary conditions. Okay, we want to estimate the boundary conditions. So the classic problem was a re-entry vehicle re-entering the Earth's atmosphere because it is coming at hypersonic velocity. mv square by 2 kinetic energy is converted to Cp delta T. Okay, because of the Cp delta T, the surface of the vehicle gets heated so much that everything will vaporize. The whole vehicle will vaporize. If you have got some astronauts inside who are trying to re-enter, the whole thing vaporizes, these people also will vaporize. So the inside compartment should be maintained at conditions where somebody can live. Or you want to design RLV, or you want to do a reusable launch vehicle, or you want to have a vehicle which can be reused. In that case, you have to design the what is called the TPS, the thermal protection system, in such a way that you will be able to recover the vehicle. What do you mean by recover the vehicle? So I will coat the re-entry vehicle with some coating of a few millimeters or something, which will ablate directly from solid. It will become vapor. It will take terrific latent heat, and there is the game I play is, since it is a high velocity, this high heat flux is there only for a short time till it hits the Pacific Ocean. Once it hits the Pacific Ocean, then we can do something, some parachute, this thing, some ship can come and they'll do all sorts of things. So it is so that time, how is the temperature proceeding? How is the heat flux proceeding? Whether it is safe, or what sort of thermal protection system you need to have. If you want to know what sort of thermal protection system, you first need to know what is the heat flux on the surface. The heat flux on the surface, you cannot put a trial rocket and measure it. Any heat flux gauge will vaporize into thin air. Therefore, even if you have to do experiment, you have to put the thermocouples at some other location. What is that location? So this is the this is the re-entry vehicle. This is the nose cone. Okay, so it is trying to enter. So what is the Q here? It's not known. So there is a solid lining. So what I do is, here I put some thermocouples. And what I do is, instead of this model, I have a complicated conduction model. So if this is the heat flux, if I solve the conduction model, it will give me the temperatures inside the solid. Then what will be the heat flux such that I get the temperatures which I measure? So this is an iterative problem. So this is how inverse heat transfer. This was the first problem Beck solved. Beck. So the need came from NASA. Okay, Americans wanted to do this. So Beck was one of the first professors who solved this. So this was what was bugging. At that time, they did not know MRI scan, this thing, cancer detection and all that. This was the problem which was bugging them. So the journey through this estimation process can be absolutely fascinating and exciting. It's a good idea to start, to have a soft start with the classic Fermi problem. This is Enrico Fermi, you know, the famous Enrico Fermi, Italian physicist, 1901 to 1954. Much of his work was in the US. So he talked about Fermi problems. In physics or engineering education, a Fermi problem is an estimation problem designed to teach dimension analysis or approximation to students instead of going through detailed model and the differential equation, boundary condition solving. So it just, which we call it as the back of the envelope or the back of the envelope calculation. This estimation technique is named after the well-known Italian physicist Enrico Fermi. Fermi was absolutely super duper in his ability to give approximate numbers. Very quickly, he can give very approximate numbers, which is fine. So there's no need to do detailed calculation. He was a ace in that. So Fermi problems typically involve making justified guesses about quantities and their variance and lower and upper bounds. See the lower and upper bounds. I told you, no, what are the lower and upper bounds for this K which you want to get? An example is what he did was how to estimate the strength of the atom bomb, okay, which he was involved with at the Trinity test based on distance traveled by pieces of paper he dropped from his hand during the blast. So from that he figured out, he gave an estimate, and he gave an estimate of 10 kilotons of TNT, trinitrotoluene, which was well within an order of magnitude of now the accepted value of 21 kilotons. So examples of Fermi questions are often extreme in nature and cannot be solved by using common mathematical or scientific information. So some intelligent guessing is required. Example questions given by official, there are Fermi competitions going on. If the mass of 1 teaspoon of class. So that was Professor Das. We just returned from Europa. Okay. If the mass of 1 teaspoon of water could be converted entirely into energy in the form of heat, what volume of water initially at room temperature could it bring to a boil? How much is the Thames River heat up in going over the dam? What is the mass of all the automobiles scrapped in North America this month? I mean, these are the questions. The most famous question is the Drake equation. You can Google it up, which seeks to estimate, are there some other intelligent civilizations other than human beings in the galaxy? Okay. So if there were a significant number of such civilizations and we have not encountered anything, then it will be a Fermi paradox. If the answer turns out to be 1, you are comfortable because according to your data, we are the only guys. So if it is more, then it's a Fermi paradox. All right. Now, his classic Fermi problem was, how many piano tuners are there in Chicago? Can we start look? Can I get some responses? How many people are there in the city of Chicago who are repairing pianos? Can somebody tell? Now, how do you see the people? Okay. So this is a classic. Are you able to see the screen and me?
Yes, sir.
Yeah. How many piano tuners are there in Chicago? This is a classic question. Any guesses? Approach.
15 to 20.
Responding. Just feel free. 100. How do you know it is 100? I'm not saying right or wrong. You tell me, defend your answer. There should be a method in the madness, as they say. Okay. So one way of looking at it would be.
So 1083.
No. Okay. Now. Okay. So some people have given different numbers, but I want you to think. It is not just a fun question. Okay. So you have to make suitable assumptions. There are at the time this question was asked, you have to say that there are approximately 5 million people living in Chicago. On an average, there are 2 people in every house. So you can make it as an average 2.53, whatever. So there, and 1 in 20 houses has a piano that is tuned regularly. And what is the requirement? What is the tuning schedule of a piano? Pianos are tuned regularly on an average about once per year. And then, if that is so, how much time does it take for somebody to tune a piano? It takes about 2 hours to tune a piano, including travel time. So, assuming that somebody works for 8 hours a day, 5 days a week, and 2 to 3 weeks, he takes his Christmas and New Year vacation. So it comes to 50 weeks of 40 hours. So 2000 hours. So please do all the math. And finally, you will get a very nice number of some 125. In fact, this was a Fermi problem. And when they actually figured out, they found out that the number of piano tuners in Chicago, according to this, it's some 128 or something. It was close to that number. Okay. So this is a beautiful way of forget about your model. This thing, all that is there. You are learning all the through your life. You're learning model analysis, equations, solving this thing, courses, all that. Sometimes you have to do some. Only then you will be able to take a risk. Only if you're a business leader or an entrepreneur, you should be able to. Okay, what is the estimate? Let me do this. Order of magnitude. It need not be 128. So, but you are sure that it cannot be 10, it cannot be 1000. It could be 128, it could be 148, it could be 98. All of these are okay. It's a reasonable number. Okay. So this is as far as the piano is concerned. Now, take the first assignment. Okay. So the assignment is like this. Write the solution on A4 sheets of paper. I'll give you the question, but before that, write the solution on A4 sheets of paper or type the solution. Write your name and roll number on the answer sheet. There are 2 problems to be given, and the solution of each needs to be written in just one A4 sheet, one side, no stories. Okay. 2 questions, 1 page for each question, just the algorithm, your method, and the answer. You either write and type it, write or type, scan, and send it. Submission will be on a link to a PDF. Link will be made by Rajesh Akula sometime today. Avoid submitting through email. Is that clear? So this is assignment 1. I'll give some weightage to this. Okay. The submission deadline is 23:59 on Thursday, 4th February. That is 12 o'clock day after tomorrow. I come again. This will be the first assignment. Write the solution on A4 sheets. Only 1 sheet per question. 1 full A4 sheet, 2 sides, 2 problems. So each of the has to be written within 1 A4 sheet. Submission to onto a link, and link will be made available by Rajesh. Okay. So what are the questions? Estimate the number of Maruti service centers in India as of 2020. We will send this if you want to take it down. Estimate the number of Maruti service centers. You don't try to Google it and give that number. I want the method. Yeah, the answer is not so important as the method. Estimate the number of Maruti service centers in India as of 2020. I'm not going to say what is right, what is wrong, and I also don't know the correct answer. We are just seeing how you think. Estimate the number of Maruti service centers in India as of 2020. Question number 2. Estimate the number of delivery agents working for Amazon in India as of 2020, last year. Okay. These are the questions. Any doubts on the questions? Okay, interesting problem. Is food for thought. I don't think other profs have started giving you quizzes or something. It's fun to work on it for the next 3 days. So that will be treated as attendance. Okay. So anybody who is joining the course has to go through this. So we will treat it as firm. People who want to do this. I did something here. Some line is coming. All right. So is it fine? Can I get some response? Are the questions clear?
Okay, sir.
Yes, sir.
Very good. Okay. So what I will do now is, Rajesh, are you there? Akula. Rajesh.
Sir.
Convert it into PDF and immediately put it both on the S-mail as well as on WhatsApp. Is that okay?
Oh, okay.
And link you can do it later. Then we will have one of the TAs evaluate it, and I will also take a look at all the answers. We will have a Google Meet and we look at all the answers this weekend. All right. So,
okay.
So the fun starts now. So just start thinking about it. So it's time for the next class. So I'll sign off. Okay. All right. Where is this now? Where? Stop share. Okay. First I will stop share. Very good. Okay. All right. So thank you very much. So first assignment already we get going. We've got nothing to do with the heat transfer. So it's just an exercise in common sense. Okay. Have fun. I'll see you at 8:55 a.m. tomorrow. Okay. With a more formal introduction. Okay. Bye.